Hi everyone, how are you doing? Okay, so today we will discuss our quiz that we just had for SVD. So let's discuss these questions. So, by the way, how many of you have attempted the quiz? Anyone here who has not attempted the quiz, or everyone has attempted already? Okay, you can just tell me frankly. Cool. Okay, so Shilpita is saying that I have not attempted. That's fine. So let's just see this question. What this question is saying that let's suppose A is written as a metric summation. I mean this is a matrix which is written as a metric summation. Now what they're saying, which of the following is not true, right? They are asking which of the following is not true. So what is the answer for this question? Okay, let's just see which of the following is not true, right? They're not asking which of the following is true. They're asking not true. So in this case, let's just see what is the answer. So, as you might remember, what are the equations for SVD? You can say AVI equal to sigma IUI, or you can also say, right? You might remember it, or you can also say A transpose UI, right? A transpose UI equal to sigma IVI, right? Okay. So, now let's just see this. Is this V2 is a eigenvector of A transpose A, where the eigenvalue is this? Yes, that is true, right? This is true because V2 is in fact the eigenvector and eigenvalue is the square of the singular value. So that's why this is actually true. But they're asking not true. Rank of this is 3. If every singular value is greater than 0, then yes, right? Because because every singular value is greater than 0. V1 transpose equal to 1. Is this not true? See, V1 is a column vector, right? And V1 transpose will be like this. So it is a matrix, okay? It is a matrix, not the scalar. So that's why this is false, right? So this is false. What about this? Yes. So if you take the transpose of this particular matrix, then the first row will be U1 transpose. And if you multiply this U1 transpose with U1, then you will be getting 1, right? So that's true. Okay. So it was easy question only. Now let's just move to the next question. Okay. C is the correct answer here. Let's see this question. So what is the answer for this question? What they're asking? They are saying that which of the following are true, right? Yes, rank of x is nothing but number of singular values, right? Which is rank of a sigma. So I think this is true. If all singular values are unique, then the SVD is unique. So we will see today that SVD is not unique, okay? So we will see this, right? So this is actually false. The first column of V is an eigenvector of x transpose x. Let's just quickly check it. I mean, if in case you forget, then you can just check it. X transpose x is nothing but U sigma V transpose U sigma V transpose, right? So which is nothing but V sigma U transpose. This is sigma transpose if you want, and then into U sigma V transpose, right? So this is just identity. U transpose U will be identity. So I think it will be V sigma square V transpose like that, right? So this is eigenvalue decomposition. Then yes, so V is basically eigenvectors of sigma transpose sigma. The first column of V. So that is true, right? This is true. The singular values and eigenvalues are same for this matrix. No, right? This is just some random statement. This is false. So what is the answer? A and C. Okay, A and C are the answers. Now let's see the next question. Okay, so what was your answer for this question? Select the true statements. Okay, about the SVD. The SVD apply to only square matrices. This is false. SVD apply to any matrix, right? This is false. Eigenvalue decomposition applies only to the square matrices. Yes, this is true, right? We have already seen this. The right singular vector of X are the eigenvectors of this. Yes, we have just seen this, right? I think this is true. The left singular vector, no, this is false. Okay, we have just seen this statement, the C statement. So I think B and C are the answers, right? B and C are the answers. Let's see the next question. Write the SVD of n cross D design matrix X as this. Okay, which of the following are true? The components of D are all non-negative. D is this diagonal matrix. So what do you think? Yes, right? Because this is the singular value. So that's true. Non-negative means greater than equal to zero, right? Non-negative means greater than equal to zero. If X is real, symmetric matrix, the SVD is always same as eigenvalue decomposition. So see, in general, there is no much relationship between SVD and eigenvalue decomposition. It is always same, then it is not guaranteed. Okay. So this is false. Okay. So see here. Uh, Yeah, this is false. Consider symmetric matrix with the negative values. For example, you take this matrix -1, 0, 0, -2, right? If you take this matrix whose eigenvalues are -1 and -2, the singular values cannot be negative. Okay. So the singular values are this, that SVD makes up the sign by making the right singular vector sign opposite. Okay, so what they're saying, the SVD is always same as the eigenvalue decomposition. So basically here, if you do the eigenvalue decomposition, this is the only eigenvalue decomposition, right? I mean, that's all. Okay, which means you can multiply the identity matrices. Okay, identity matrix. This is basically the eigenvalue decomposition. But the SVD will be different, right? SVD will not be having negatives as singular values, right? So which means, see what they're saying. Suppose you take some symmetric matrix, for example, this is some symmetric matrix. Okay, diagonal matrix basically. The EVD, eigenvalue decomposition, is basically says that you have let's suppose a u, then it will be u lambda, which means a is basically u lambda a u inverse, right? Where lambda is some diagonal matrix of eigenvalues. So now you tell me, if you have this as a, isn't it same as you write identity matrix here -1, 0, 0, -2. I mean, the eigenvalue decomposition of diagonal matrix is basically just the same, right? For example, this is the eigenvalue decomposition. Now, if you write the SVD, can you have the same SVD? Can you have the same matrix in the middle? Is this possible? No, right? Because the singular values cannot be negative. Okay, so SVD cannot be same as this, right? Is this fine to everyone? Okay, so because this cannot be in middle for SVD. In general, there is no direct relationship between SVD of any matrix and EVD of any matrix, right? Okay, so Hers is saying what is a design matrix, right? The SVD of n cross D. Uh, I think it is something like the design R matrix. Okay, something like that. There is nothing called design matrix. It might be design R matrix or something. Okay. Anyway, so now let's just see the option C. The columns of V have all unit length and orthogonal to each other. Yes, right? So that's true. And columns of D are orthogonal? No, obviously that's not true. So I think this is true. SVD need not to be same. In fact, there is no direct relationship. Okay. The columns, yes, this is true. This is false. Okay. So I think A and C are the true. Sorry. The columns of D are orthogonal to each other. D is a diagonal matrix. Yes, yes, yes. So basically, for the diagonal matrix, if you have anything, for example, actually this component will anyway get multiplied with zero, right? You can have anything here, x1 0 0, and then x2 0 0, something like this, right? So this component will always get multiplied with zero. So these are orthogonal to each other. Yeah, that's a nice catch. Okay. Okay, so this is true. So Ajay is asking, sir, if D has two zero columns, can we say they're orthogonal? Uh, yeah, actually, by definition of orthogonality, it has to be just UI transpose into VI, U1 into V, U1 dot product with B should be zero. This is the definition, mathematical definition of orthogonality. So the case you are saying that if these are the two zero columns, actually zero is some special column. It is satisfying, right? It is satisfying this orthogonality. So you can say it. Okay. It is satisfying the definition. So as per the definition, you can say it. Okay. Now let's check this. So what they're saying, if X is this, then which of the following matrices have eigenvectors? Following matrices are the eigenvectors of columns U. So let's just check X transpose. I think it is X transpose, right? So X transpose U D V transpose because U is coming at first, right here. So U into U D V transpose, right? So it is U D V transpose V D transpose U transpose, something like this, right? Yeah. So I think it will be identity. So it is U D square, something like that. U transpose, right? So basically it is eigenvalue decomposition of X transpose, right? So this must be having the eigenvectors, right? This is eigenvectors of X transpose. So yes, X transpose, eigenvectors of X transpose are in this U, right? Okay. What about X transpose square? Eigenvalue, if you remember, for the square matrix, right? Eigenvalue get square from lambda to lambda square, but the eigenvector remains same, right? For the square matrix. If A is having lambda and x, then A square will be having lambda square and x, right? So for D also it is true. Is this true for A? No. X transpose X basically, like eigenvectors of X transpose X are kept in V, right? Are kept in V. Okay. So these two are answers. C or D, C and D are the answers. Now let's just check this problem. So how many of you were able to solve this question? Let me know. Okay. So Diksha is saying that she was able to do. Yes is saying that I was not able to do. Okay. So that's not very hard question. It is easy only. So what they're saying that let's suppose this H is given something like this. Is this a singular value decomposition? Tell me. No, right? Is this SVD? Then answer is no. Okay. But I think they are perpendicular to each other. I mean, they are orthogonal. They are also orthogonal, right? So these are two orthogonal matrices, and in between you must be having the diagonal matrix. So it is just that you need to make them orthonormal, right? So what is the length of this? Square root of 1 square plus 1 square plus 1 square plus 1 square. The length of this is square root of 4, which is 2, right? So what you can do, you can divide with the length of this, right? You can divide with the 2, okay? By 2 by 2 by 2, okay? So which means what I'm trying to say here is that if you divide with the 2, then this matrix will become the orthonormal matrix, right? I mean, the first matrix. So if you divide everything by 2, right? I mean, if you multiply by 1 by 2, then obviously you need to multiply by 2 also, right? So you can multiply by 2 also. 2 you can adjust, I think, somewhere here, right? 2 you can adjust here. Okay, you can multiply 2 also. So basically you are multiplying by 1 by 2 and you are also multiplying by 2. Is this fine to everyone? Okay. Now, now basically, see here what you're doing. These are the three matrices, right? So you are multiplying by 1 by 2 here. Okay. You are multiplying by 1 by 2 and then you are adjusting the corresponding entry here by multiplying by 2. Okay. Now This also has the length of 1 by 2, sorry, length of 2. Then you are also multiplying by 1 by 2 for this, and the corresponding 2 are multiplying here, right? What is the benefit of this? This is a matrix multiplication. So this scalar will get multiplied to only one of the row or one of the column. Okay. Is this? Tell me. Okay. So what is wrong in this? So basically, if I'm multiplying by 1 by 2, then it will automatically this first 1 by 2, it means you are multiplying by the whole matrix, right? You're multiplying by the whole matrix. So fortunately, this also had the length of 1 by 2. So it means that both are sharing the same length. So if you multiply by 1 by 2, then it is also having the unit length. Now it will also have the unit length, right? Now what is the length of this vector? Square root of 4 plus 4, which is square root of 8, which is I think 2 into 4 square root, which is 2 root 2, right? Length of this vector is 2 root 2. So you need to multiply by, these both are having the same length, 2 root 2, 1 by 2 root 2. So similarly here you will multiplying 2 root 2, right? So which means you ultimately multiplied 4 root 2 here. And now this is orthonormal. This is also orthonormal. So 4 root 2 have multiplied. Now if you multiply 4 root 2, then it will be 4 into 4, 16. This is 8 into 4, 32. So what is the largest singular value? 32. Okay. Generally we keep them in the decreasing order. But it's not very hard and fast rule. Okay. So I mean I will prefer if they keep it in the decreasing order. So you always take it in the decreasing order only. Okay. So basically 32 root 2 should be the answer. Okay. Okay, got it. So, some of the people are asking that this U is basically not a square matrix. Yes, actually, this question I will rephrase this question. If sometimes like they just write the truncated SVD. So if this is not a square, you can consider like this. I mean, there are, let's suppose, two more columns of zeros, and then this will be, I think this is 4 cross 4, right? And this will be also 4 cross 4, so something like this, 4 rows. Okay, so basically you can make it a square by putting the zeros, and corresponding zeros will be here also. So ideally it should be like that in the question itself, but sometimes they write it truncated SVD. But anyway, I will modify this question a little bit. Okay, so this is truncated SVD which is given to us, or some people call that economy. Okay, economy SVD. But anyway, I will modify this question and make sure this U is square matrix. Okay. Okay. So let's not worry about this question. I will just rephrase this question more once more. Now let's just see this question. What this question is saying. Let A be the symmetric matrix. Eigenvectors of A, which corresponds to the distinct eigenvalues, are always, for the distinct eigenvalues, they're always obviously linearly independent, right? And if they're corresponding to distinct eigenvalues, then they're orthogonal also, right? Do you remember this? If they're corresponding to the same eigenvalue, then they need to be orthogonal? If A is symmetric, right? Then in that case, in that case, if you say that okay, eigenvectors, all eigenvectors are linearly independent, right? Then you will say all eigenvectors are linearly independent. This is the first thing. The second thing on top of that, you can say that if eigenvalues are different, then corresponding eigenvectors are orthogonal also, right? Okay. So corresponding to distinct eigenvalues, linearly independent, orthogonal. By the definition of eigenvector, they are non-zero, right? They're always non-zero. So A, B, C are the correct answer here. Now let's just see this. I think this was also easy question, right? So they are saying left singular vectors are A transpose A transpose A. Which one is true? A or B? See, A is basically starting with U, right? So yes, so basically U vectors are basically in A transpose. Okay, you can even multiply A and A transpose. You will be getting U sigma V transpose into, and then you can see that okay, if you multiply A and A transpose, you will be seeing that okay, eigenvalue decomposition of A and A transpose, having U as eigenvectors, right? So that's why this is true. What about this? The left singular, this is false. Each column of U is a scalar multiple of one or one of the standard basis vector. That is not true, right? Each column of U has norm. Norm means length, okay, equal to its corresponding singular value. What do you think? No, right? It is always one. So that's why I think only A is true. Okay. Now let's just see this. So what they're saying, consider the following matrix and its singular value decomposition, which is given like this, right? Let X be R3, be in R3, be a unit vector such that length of AX is maximized. Okay. So then what will the length of A plus be? See, you are multiplying a vector with a matrix A, right? Now they are saying that you want to maximize, okay, its length. It's a unit vector to start with. Now ultimately you want to maximize its length. So basically, as you know that if you are multiplying by let's suppose any matrix, then first if you are starting with v1, let's suppose v1 v2, then after multiplying by the v, they get rotated, right? So initially, let's suppose this is v1, this is v2, right? Then after multiplying by the v, they get rotated, and then this is, you can say, after multiplication by v transpose, okay? And then you multiply by sigma. So what does sigma do? Sigma takes any vector, let's suppose x1, x2, x3, and then it can make it sigma 1 x1, sigma 2 x2, sigma 3 x3. So if you're aiming for the highest value, then everywhere it should be sigma. And which vector has that? If you start with v, right? If you start with v1, then if you multiply, I mean, if you multiply by the for example, this a v1, right? A v1 will be u sigma v transpose v1. So what is this v transpose v1? This is just one all zeros, isn't it? Right? So this is just u sigma one all zeros. And then if you multiply with this, then it will be u sigma 1 all zeros, right? And then this sigma 1, this will get multiplied with this matrix u. Or maybe if you want, you can from here itself, you can find out the length of a sigma 1. It is AB1, it will be sigma 1 only. So basically for the highest, for the highest change, you need every of this parameter to multiply by sigma 1. That is possible only when you have one all zeros, right? Because this get multiplied by sigma 1, this get multiplied by sigma 2. So you don't want to get multiplied by sigma 2, right? You want to take sigma 1 as common. So that's only possible whenever you have one all zeros, which means that's only possible whenever you have v1 here, which means if you multiply by the v1, then I mean any unit vector you have here, okay, from the geometry also you can see this is the set of all unit vectors, right? This is the set of all unit vectors. Now only v1 is the one which get stretched, okay? So after the multiplication of the sigma, this v1 is the only one which get stretched too much. And how much it gets stretched ultimately? With the value of sigma 1, right? This is sigma 1, this is sigma 2. So this is basically v1, and then this is, you can say, v transpose v1, this is sigma v transpose v1, right? And then again it will get rotated, okay? I mean multiplying by u does not change the length. Do you remember? Multiplying by the any orthonormal matrix does not change the length, right? So again it will get rotated. So basically v1 is the only one which get stretched too much, Okay, v2 is the next one which get stretched. I cannot say, I mean, like, if the vector is more close to v1, for example, if the vector is very very close to v1, okay, let's suppose if it is not exactly v1, then if it is very very close to v1, then it will be here also very very close to v1, and then it will be here also very very close to v1. So basically, if a vector is very close to v1, if not directly v1, then if it is very close to v1, then it will be stretched too much, right? If it is v1, then it is the maximum stretch that you will be getting. Okay, so from all the unit vectors, v1 always get too much stretch. So so basically they are saying if x is a unit vector such that ax is maximized, so which means x must be v1. Okay, this particular statement infer that x must be v1. Then what is the value of a plus b? So b1 is this, right? B1 is this, I think. Sorry, this is v1 transpose. Okay, so basically b1 is this one, right? So if you add these two, I think it will be 1 upon root 3. A plus b. Okay, sorry, it is a plus b. You will be getting 0, right? So what is the answer here? Okay, I think I haven't mentioned the answer here, but it should be 0. Can you check the answer? Okay, b is given, right? Cool. So answer is 0. Okay. Okay. Now let's see this. What they are saying. A certain 2 cross 2 matrix A has singular value decomposition, something like this. Consider vector v1 plus 3v2. What will the length of ax? Okay, you just need to multiply with the a here. A means u sigma v transpose, right? So if you multiply a into x, which is u sigma v transpose into v1 plus 3v2, then what you will be getting? See, this v transpose v1 is just a first standard vector, and then multiplying with this sigma will get you sigma 1 all zeros. Okay, let me do step by step. See, this is u sigma v transpose v1 plus u sigma v transpose capital V. This is capital V, right? Capital V transpose v2. So if you write capital V transpose, which means this is v1 transpose, this is v2 transpose, like this, right? If you multiply this with v1, then you will be getting the first standard vector. If you multiply this by v2, then you will be getting the second standard vector, right? So it will be the first standard vector multiplication by u sigma and first standard vector, right? So it will be something like this. And then you will be multiplying with the sigma 1. I think say it will be sigma 1. Okay. Yeah, outer product could be easy, right? In this case. But anyway, let me first do in this way. Something like this. Now, if you multiply this, if it is u1, u2, u3, if you multiply with this sigma 1 0 0, then this will be sigma 1 into u1, right? Plus, so basically it will be sigma 1 into u1 plus 0 plus 0. So it is just sigma 1 into u1. Similarly, it will be a sigma 1 into u2, sigma 1 u1 plus sigma 2 u2. Okay. Now they are asking length of this. So what is the length of this? How to calculate it? What is the length of this vector ax? Sigma is the length. How? The rank of A is 1. Okay, so we can take a help of column space, row space, etc. They may seem to be perpendicular. AX is in the column space. Okay. Okay. So actually here the sigma 2 is given as 0. Since the sigma 2 is 0, so you directly have this as sigma 1 u1. So sigma 1 u1 is there, and if you find out the length of this, length of u1 into the value of sigma 1, right? So it is just sigma 1. Sigma 1 is 2. So that's why the answer is 2. Okay. So length of the vector AX is 2. You can also do in this way that A is A into V1 plus 3 V2, right? This is nothing but AV1 plus 3 AV2. Then AV1 is nothing but sigma 1 U1 plus 3 sigma 2 U2, right? AV1 is sigma 1 U1. Okay. So that is why you will be getting that as 0. Oh, sorry, the sigma 2 as 0. That is why it is just sigma 1 U1. Okay. In this way also you can do. Okay. Now let's just see this. This is question number 11. So what they are saying, what is the dimension of null space of P? Okay. So what is the nullity basically they are asking, right? So what is the rank of this P? P is 2 cross 3 matrix, right? 2 cross 3 matrix. Rank is 2. Okay. So rank is basically 2. Why? Because there are two non-zeros, singular values, right? Because there are two non-zero. So what about nullity? How many columns are there total? 3 columns. So nullity will be 1. Okay. That was easy question only. I hope you understood. Now let's see this. What are the answers for this? Can you tell me? They're asking which of the following are true, right? Okay. So if A and B are the similar square matrices, then every singular value of A is also the singular value of B. If they are similar matrices, suppose A and B are the similar matrices, right? Maybe you can take how we define the similar matrices. Do anyone remember? A is B, some diagonal matrix, something like this, right? Do you remember this? So now they are saying that A and B are the similar matrices. Then every singular value of A is also the singular value of B. What do you think? So let's just write B as this. Okay. So this is true or false? Let's just write A as U sigma V transpose. So it will be du sigma V transpose D inverse, right? Okay. Now basically, if this du is orthogonal, right? Orthonormal matrix, and this is also orthonormal matrix, which means there is no change to sigma, then only I can say this. But I don't think there is that is true in general, right? So just a second. So basically, if you have this, this is B, right? Then they will be sharing the singular values only when the sigma is intact. I mean, B is also having something like this, right? Some orthonormal matrix sigma into some other orthonormal matrix. But it is not obviously guaranteed that if you multiply by the diagonal matrix, then it will be also orthonormal, right? Similarly, it is also not needed that it will be also orthonormal. So obviously it is not making any sense. So here, what is the answer for this 12? This is false, right? Also, let's suppose that instead of singular value, I have eigenvalues. Then for the similar matrices, eigenvalues are same, right? For the similar matrices, eigenvalues are same. Okay. What about this? If A is invertible and sigma is singular value of A, then 1 upon sigma is a singular value of A inverse. Okay. You can take the A inverse and then you check it. This is V transpose inverse, right? So since it is orthonormal matrix, that's why it is just, inverse is just transpose. So it is sigma, it is just transpose. Okay. So because it is orthonormal matrix, right? So that's why like this is 1 upon sigma. Okay. So 1 upon sigma is the singular value of A inverse. So that is true. A non-zero singular value of AB and B are same. Non-zero eigenvalues are same, but singular values need not to be. Okay. So this is also false. Eigenvalues, this is true. So B and D are the correct answers, right? Okay. For the singular value, you can check basically AB and BA. You can multiply AB and BA. And obviously, like let's suppose this is U sigma V transpose. This is, let's suppose, X sigma 2 Y transpose, something like this, right? I mean, if even if you multiply something like that, then it need not to be the case that in between whatever is the matrix you are getting here, and you will be getting the same kind of matrix here also, right? Okay. Let's see this question. It was, I think, easy question only. So what is the answer here? Say these are the n linearly independent, but now you have n minus 1 linearly independent, right? So that's why it is D answer. Okay, let's see this. This is little interesting related to the outer product. So basically the questions that I have given in this quiz, I just made sure that from the basic to middle concept to the advanced concept, everything is covered. If you have noticed, then I have given a question related to geometry, right? Geometry of SVD. How that if you use V, then this AX is maximized, right? I have given the question related to geometry of SVD. I have given the basic question also. I have given the questions related to the outer product of SVD and so on. So I want to cover. I wanted to cover all the possible variations of SVD. Okay, as per the gate required. Okay, so what they're saying? Let's suppose P is something like this. Now, you know the outer product, right? Outer product looks like this: sigma 1 u1 sigma 1 u1, or yeah, u1 b transpose, right? v1 transpose plus sigma 2 u2 v2 transpose, something like this, right? The outer product looks something like this. So this is sigma 1, most probably this is u1, most probably this is v transpose, right? But it is obviously not having the length 1. Okay. These are orthogonal, u1 u2, these are also orthogonal, but it is just the case that this is not unit length, right? Let's just make it a unit length. So what I need to divide here, what is the length of this? 36 and 64. This is 100. So I think 10. So if I divide by 10, then I will multiplying by 10 also. So 1 by 10 you can multiply here, 10 you can multiply here. So it will be 2. So I think sigma 1 is coming as 2. Similarly, sigma 2, if you multiply by 10, then sigma 2, basically you need to write it. I mean, you need to call this as sigma 1 actually. I mean, the higher value we call that sigma 1. Okay. Anyway, so this is sigma 1, this is sigma 2, right? 2 and 4. So I think 6 should be the answer. Okay. It was also easy question. Just that you should be knowing that how to write in the outer product. Okay. The only reason I have given this question just to make sure that you know that how to write in the outer product. See, this question, by the way, I have taken from Berkeley University. Okay. So the only reason I have given it is just to make sure that you are little more familiar with the outer product. Okay, all of these questions, for example, this question also from Berkeley University, all of these questions, right, are from some standard university. For example, this is Berkeley, this is also Berkeley, this I have not written the source, that's fine. This is from Duke University, this is also okay, this is from some university. So all of these questions, okay, this is from NPTEL, from some standard resources, this is from Berkeley, and so on. And from Stanford also I have taken some questions. For example, this question is from Stanford. Okay, all of these questions are from some standard universities from here and there. Okay, now let's just see this, what they're saying. Consider a 4 cross 3 matrix, something like this. Okay, form a set of orthogonal vectors satisfying the length of the first vector, length of the second, length of the third. Okay, let sigma 1, sigma 2, sigma 3 are the singular values of this matrix. Then what is this? A sigma 1 plus sigma 2 plus sigma 3. So these are orthogonal already. What you can do, you can make them orthonormal, right? So you can divide by 3, right? So this a1 divided by 3, a2 divided by 2, and a3 divided by 1. So, okay. So what does this mean? How you can divide by 3? If you want to multiply by something like this, then how you can multiply? Can you multiply by 3 in just this, 2 in this, and 1 in this by just one scalar? If you multiply by 3, then it will get anyway multiply by all of them, right? So I think if you want to do something like this, right? Suppose you want to do something like this, then what you can do, you can multiply by some matrix. So how does that matrix will look like? 1 by 3, I think if you write here, right? 1 by 3 if you write here, and 1 by 2 if you write here, 1 if you write here. If you multiply these two matrices, will you be getting this matrix? Tell me. Will you be getting this matrix? Yes, right? Okay. Because this is 1 by 3 into this column and 0 into this, so I think you will be getting this matrix. Now, just for the writing, let's just say that at the end, you are multiplying by the identity matrix. Okay. So suppose at the last, you have identity matrix. Okay. So now, what you can do, see this particular thing is a singular value decomposition, or not exactly the singular value decomposition because these are not orthonormal yet. So what you can do here is that, so just write like this, right? So instead of this, basically I want the singular value decomposition, right? So I can make them orthonormal, and let's just multiply by 3 and 2 here, and this will be just like this. So given matrix, which was a1, a2, a3, can you write like this? This a1, a2, a3, something like this. Is this okay to everyone? Yes, right? So basically, this particular decomposition is the singular value decomposition. Is this orthonormal? Yes, unit length and orthogonal, right? It is anyway orthonormal, and that's why this is a SVD. So now you can tell me what are the singular values? Sigma 1 plus sigma 2 plus sigma 3. This is 3 plus 2 plus 1, right? Which is 6. Okay. Ajay is saying that can we find the eigenvalues of A transpose A? Yes, you can do it, but actually the question, the reason I have put the question so that you can, don't do much calculation. You can rewrite it in some way such that the SVD is visible. Okay. So I think 6 is the answer. Yes. This question I have taken, let me just tell you, from Berkeley University. Let me just open this up. Okay, they have actually found out the eigenvalues of A transpose A. They've actually did A transpose A, and then they have found out the eigenvalues of A transpose A. But okay, that's fine. But actually, that was not much needed. Okay, this is the solution. But yeah, that was not much needed. You can do in this way also, right? Now with some practice, you know that okay, if you want to for example, if you want to remove this 3, this 2, and this 1, so basically different constants, so a matrix will work, right? One matrix will work. Okay, so Diksha is saying, sir, what does this 2 along with a1 e2 a3, where it is written 2 along with a1 e2 a3, somewhere here, where does this even written? Okay, so Bachu Paul is asking, sir, can you please share all of these resource link? Actually, it's not needed. I mean, in always a test series and in everywhere, you will be finding some questions from the different resources. So if you want, we can share, but it's not much needed. Okay. So if you want, I can share it with you guys, but it's not much needed. Actually, whatever is relevant, we have already taken it. Okay. So you will be just end up wasting your time if you look at these resources and all. We have taken it already. Okay. Let's see this question number 16. So what is the answer here? So what they're saying is that let A be a 4 cross 4 matrix that can be decomposed something like this. Okay. It has been decomposed something like this, where P is orthonormal matrix and S is symmetric matrix. The given A, H full singular SVD, where the P and S. So they are saying that A is a matrix which can be decomposed into orthogonal. This is orthogonal. Okay. And this is symmetric. Okay. So in terms of U sigma V transpose, okay. So what is what is this P? What is this S? So if you take P as U V transpose and S as V sigma transpose, V sigma V transpose, then does this P into S give you A? Yes, it is giving you A, right? The first check is that P into S is A. The second check is that is P orthogonal? Is P orthogonal? Is S symmetric? S is symmetric, right? S seems to be symmetric. Hmm. But is this orthogonal? U into V transpose. Need not to be, right? It could be like there is anyway no relation between U and V. Okay. I mean, the eigenvectors doesn't have any relation. Eigenvectors of AB and BA doesn't have any relation. So U and V could be anything. So it need not to be orthogonal. Okay. P is identity matrix. S is this. Is this orthogonal matrix? Yes. S is this, but P into S is this giving you A? PS is not A, right? Okay, PS is not A. Here, PS is A. Is this orthogonal? U into U transpose. Is this orthogonal? Orthogonal means, what is the definition of orthogonal? It means that if you multiply the transpose of this itself, okay, transpose of this itself, then it should give you the identity matrix. Let's just check it. Okay. U transpose U transpose. So U transpose U. Uh, this is U transpose. Yeah. U transpose U is identity. But this U transpose. Just a second. This okay. U is a square matrix here, right? Yes. So here, since it is 4 cross 4, so here U is a square matrix. Okay. So if it is a square matrix, then U into U transpose itself is identity. Okay. If it is a square matrix. If it is not a square matrix, then U transpose into U is identity, but U into U transpose need not to be. Do you remember? In previous class also we have discussed this. If U is ortho normal, if it is square, then U equal to sorry, U inverse equal to U transpose, basically the inverse exists, right? Inverse exists. So in that case, U into U transpose into U equal to everything is identity. If it is square. If it is not square, right? Not square. In that case, U transpose into U is identity, but U into U transpose is not identity. Okay. Obviously, both cannot be identity. Why that is the case? Because let's suppose this is 2 into 3. So what is the dimension of this? 3 into uh sorry, this is can it be 2 into 3, by the way? 2 rows, 3 columns. This cannot be linearly independent, right? So let's just take it 3 into 2. Okay, just a second. Let's just take it 3 into 2 because it cannot be 2 into 3. Let's just take it 3 into 2. This is 2 into 2. This is 3 into 3. Can you tell me both can be identity? Do you remember eigenvalues of A, B, and B must be same? So the eigenvalues of this are only two non-zeros, right? Right? Here, if this is also identity, then eigenvalues will be three non-zeros. Is this possible? Tell me. So basically, what I'm saying here is that this has two non-zero eigenvalues. It cannot be identity 3 cross 3. Otherwise, three non-zero eigenvalues, right? Which is not possible. So anyway, if it is a square matrix, then inverse exists. Then it is okay. Then it is same. But if it is not a square matrix, then U transpose into U is identity, but U into U transpose is not identity. Okay. So U into U transpose is identity only when it is square matrix. But here it is square matrix. So anyway, this is identity, right? Okay. So this is definitely orthonormal. Is it symmetric? Is it symmetric? S V sigma U transpose, right? So I think this need not to be symmetric. Okay. So what is the answer that I have given? A. Okay. The product of two orthonormal matrices. Can you just check whether UV transpose into UV transpose is identity? UV transpose. Oh, this is actually identity. Okay. Okay. So yeah, this A is true. Actually, by mistake, I made it wrong. But sorry, A is actually true. Okay. Because this is basically the orthonormal matrix, right? This is the orthonormal matrix. Although there is no relation between the eigenvectors of U and B, but yeah, this is the orthonormal matrix. You can just check it. How? UV transpose into the UV transpose must be identity. You can just check. Actually, it is identity. So that's why this A is true. Okay. Cool. Now let's see this question. What they are saying: what is the largest singular value of this particular matrix? I mean, this is a vector, but you can consider this as a matrix also. What is the largest singular value? Which means you need to find out the eigenvalues of A transpose A, okay, or A transpose whatever. Suppose this is you are finding eigenvalues of A transpose. Then don't you think this will be a little hectic task? So instead of that, let's just find out the eigenvalues of A transpose A, because anyway the eigenvalues are same, right? Minus non-zero, at least the eigenvalues are same. So what are the eigenvalues here? I think this will be 25, right? 25. So the what is the singular value then? Singular values must be, the two singular values must be 5 and 0, right? Okay, because the eigenvalues here are of A transpose is basically 5 and 25 and 0. Okay. So 5 is the correct answer here. Okay. I have not written the answer, but that's fine. This question was from Stanford. Let's just check this. See. Okay. So 5 is the answer. Let's just see this question number 18. Okay. Let's see how to solve this question. So what they're saying, given this matrix with the singular values of this, B with the singular values of this, AB, they're saying that AB is some matrix, right? Suppose C has the full SVD, which is something like this. And this is a representation, which is saying sigma 1 to sigma 6. We allow the possibility of some of these singular values to be 0. How small can sigma 1 be? Okay. So C is constructed like this. They are saying C is constructed like this with A, right? With A and with B. Their singular values are given 753 and this is 221. Okay. So what is the smallest value of sigma 1? What is sigma 1? Sigma 1 is the first singular value, right? Did anyone solve that question? So let's see that how they have solved this question. So what they're saying, taking u to be the right singular vector of A associated with this largest singular value is 7 and v is a 0, then we find out length of this v and 0 equal to 1, u and 0 and AB. Okay, this shows the norm of C must be at least 7. Can it be 7? The answer is yes. Just take singular value C. Okay, so they're asking the smallest possible value of sigma 1. So how you can do this question? Let's just think about it. Actually, this is little bit related to the partition matrix also. Okay. I mean, the way these matrices are written, basically this is related to the partition matrices. So let's just do one thing. Let me just cover the partition matrix, which is really easy. And then you will see that, okay, how to multiply, if these are the partition matrices, then how to multiply a vector to this partition matrix and so on. Okay. So just a small topic that I will cover tomorrow, which is called partition matrix. And after that, I will solve this question. Okay. Let's move to the next question for now. Okay. So what they are saying here, that which has the eigenvalue decomposition is given like this. And then they're asking that what should be the SVD. Okay. So fortunately, I think this is symmetric matrix. So that is why these are actually the orthogonal. Okay. Fortunately, they seems to be the orthogonal. Okay. So and the norm here is 1/2 plus 1/2. Norm is also 1. Okay, great. So they're orthonormal also, norm is 1 also. So which means A is W D W transpose or W inverse, right? Because this is orthonormal anyway. Now, this is eigenvalue decomposition, and singular value decomposition looks something like this. Okay, V, I've written just V. Okay, so generally it should be V transpose. Okay, because of this answer will change, right? Should be V transpose. I mean the general notation I'm writing. Now U should be same as W. Sigma should be same as D. V should be also same as W. So I think that case C is the answer. But if you're writing just okay, if you're writing just V, let me just check in the original source what was written. Okay, this is a Berkeley question. Okay, they have written V transpose, right? Okay, then this is the answer. Okay. Anyway, so if you if you got the answer, that's fine. But if you write V here only, then it will be V transpose W transpose. Then it is A. Otherwise, it is C. Right? If you only write V here, then it should be A. Right? Then you will be taking the transpose. If you write V transpose here, then it should be C. Okay. Based on that, you can write it. Okay. Yeah. So as per this question, it should be A only, right? So let's not write the transpose as per the question. As per this question, it should be A only. Okay. Okay. Now let's solve this question. This is a little more interesting question than any other question, which is related to number of different SVDs, right? How many SVDs are possible? So let's just cover this small topic, that number of different SVDs. Okay. And then we will see that question. Suppose that A has some SVD, which is U sigma V transpose. Now U is orthonormal, right? V is also orthonormal, and also we know some relationship between, for example, A and V, right? Something like this, right? Some relationships also. So now suppose there is U, which is basically, let's suppose U1, U2, something like this, right? U3. Can you okay, one thing you might be knowing, that if X is eigenvector, then Kx is also eigenvector. Do you remember this? Do you remember this? That X is eigenvector, then Kx is also eigenvector, right? It is very easy to prove. Ax equal to lambda x. You can multiply K both sides, right? Okay. Now these are the eigenvectors, right? Of A transpose, eigenvectors of A transpose. But if U1 is eigenvector, can I also write 2U1 here? Tell me. Can I also write 2U1 here? Because these are just eigenvectors. What do you think? They will be anyway orthonormal. I mean, at least the orthogonal will be there. Yeah, orthonormal will not be there. Okay. So you cannot write 2 here, right? You cannot write any arbitrary number here. 2 is not possible. Why? The moment you multiply by 2, then the only problem is that the whole length of this vector will be 2, not 1. But you want the 1, right? But can you multiply minus 1 here? Yes, right? We can multiply minus 1 here. So what you can do, if you also remember, from the outer product also you can see, right? From the outer product also you can see something like this. So if you multiply -1 here, then to adjust this -1, you can multiply the same -1 with whom? Ultimately this will be adjusted with v1, right? Sigma also you can't do anything because sigma is not negative. So you what you can do with v1 also you multiply by -1. Okay. Which means if you choose to multiply -1 here, then you can multiply -1 here also. Then this is also the valid SVD. So if what I'm trying to say is that if a equal to u1, u2, u3 into sigma into v1 transpose, v2 transpose, let's suppose v3 transpose. Okay. If this is a valid SVD, right? If this is a valid SVD, then this is also the valid SVD. Minus you can adjust here. Okay. Ultimately, this minus and minus, ultimately this will get cancelled out to be plus. Why? Because the outer product also, from the outer product also we can see sigma 1 u1 v1 transpose. So if you are multiplying -1 here, you multiply the same -1 here, it won't impact anything, right? You can't multiply -1 to sigma 1, so that's why I multiplied to that. So basically, if you're multiplying -1 here, corresponding -1 could be there. So let's not worry about it. I mean, this could be the corresponding minus you can write. So whenever I'm counting, okay, in the counting it won't matter. For the v it won't matter. So let's suppose these are the n. Okay, these are the n vectors. So for example, if this is m cross n, then this will be m cross m. But for example, let's suppose uh, this is a square matrix. Okay, for example, let's suppose this is n cross n only. So these will be basically n vectors, right? So here in the given question, it is a square matrix of 3 cross 3. So let's just take the simplest case. Suppose this is a square matrix. So these are the n vectors, right? Similarly, these are the n vectors. Now, can you tell me that if you can multiply -1 here, you can multiply -1 here, right? So can you tell me how many different possible SVDs are there in this case? See, you can choose to multiply -1 or not, right? So there are two possibilities here. Similarly, there are two possibilities here. Similarly, there are two possibilities here. And then corresponding -1 you can write anyway here. It doesn't really matter. Okay. I mean, there is just one choice here. Okay. Like based on that, you will be writing the minuses here. So basically, you can say there are 2 power n different SVDs are possible. Okay. There are 2 power n different SVDs are possible. Is this fine to everyone? Why? Because you can choose to multiply -1 here or may not multiply -1. If you choose to multiply -1 here, then you need to multiply -1 here. If you choose to multiply -1 here, then you need to multiply -1 here also. Why I'm just multiplying -1? Why not any other number? Because see, because as I know that if x is eigenvector, then kx is also eigenvector. So why only -1 is working? Why not any other random number? Because the vector's length must be 1. Ultimately, the length must be 1, right? Okay, cool. Now let's just solve this question. This question is actually now finished. So if these are 5, 4, 2 are the different distinct singular values, then how many SVDs are possible? 2 power 3, right? 8 SVDs. Okay. But there are different cases here also. Suppose, suppose I write, right? Suppose I write A as sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose. Similarly, sigma n un v n transpose. Suppose you write something like this. Okay. Now, now suppose, for example, this particular value. Okay. For example, let's suppose this particular value is 0. Okay. This is 0, right? Now you tell me. Now you tell me. In that case, if this is un, and let's suppose this sigma n is 0, this is vn, then, and let's suppose this is not 0. Okay. Everything else is not 0. Only one of the value is 0. In that case, if we multiply minus in this u, okay, if we multiply minus 1 here, will it really matter ultimately? If you don't multiply here, okay, you don't multiply here, but you only multiply in u, ultimately will it matter? If you only multiply in this u, doesn't really matter. See, earlier, if you multiply in this u, you also need to multiply in v. Okay, it is forced. But now, if this sigma is 0, okay, if this sigma is 0, then if you're multiplying only in this u, then multiplying v is optional. So basically, in this specific case, where only one of the sigma is 0, okay, only the one sigma is 0. Only in this specific case, okay, I will tell you more cases, but in this specific case, how many total SVDs? See, till now there are n minus 1 vectors, right? So 2 power n minus 1 SVDs into how many choices you have for u? Basically, now for each of this, you have how many choices? You take, I mean, you take here, you don't take here. Basically, this is un, this is vn. Okay. Plus, 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 minus, minus, plus, minus, minus. Basically, there are 4 choices. Okay. For each of this, you have 4 more choices. Getting my point? Basically, it is independent of whether you are putting minus here. You can put or you cannot put. Right? So ultimately, in this specific case, when only one of the sigma is 0, then this is 2 power n plus 2. Okay. If only one of the sigma is 0. Right? Now, let's see one more case. Okay, sorry, it is n plus 1. Yes. Now let's just see one more case where multiple sigmas are 0. Okay. Or maybe let me write in general where multiple, I mean, or let me write like this, sigmas, okay, are repeating. So earlier my assumption here is that, okay, only one sigma is 0 and all sigma are distinct. Okay. Why, I will tell you. Suppose sigmas are repeating, right? Which means what is this sigma, or maybe what is this sigma square? Eigenvalue of A transpose A, isn't it? Now you tell me, if the sigma squares are repeating, in that case, what will happen? You will be having, see, this is symmetric matrix, right? Now suppose one of the sigma, let's suppose sigma 1, okay? This is repeating 3 times. Now corresponding to this sigma 1 square, how many linearly independent eigenvectors? If this is symmetric matrix, then for the symmetric matrix, AM and GM both are equal, right? 3 linearly independent eigenvectors, right? If this is symmetric matrix. Now, if this sigma is repeating, right? Then in that case, what will happen? You will be having corresponding to sigma 1, you have 3 linearly independent, right? Okay. And then you can make them orthogonal also using Gram-Schmidt, but let's not worry about it. But suppose you have 3 linearly independent. This is, let's suppose, sigma 1, this is sigma 1, this is sigma 1, right? Now you will be writing first vector, second vector, third vector, right? You will be writing these vectors like this. Okay. Now, let's suppose those three vectors are like this. Okay, the solution looks like this. C1, maybe P, C2, Q plus C3, R. Let's suppose these are the eigenspace or the eigenvectors corresponding to sigma 1 square. Okay. Okay. Now you need to write some one of the vector here, one of the another vector here, another vector here. Okay. Tell me how you will be writing. So in the sense, you can write P here. Is this fine? And you can normalize this P, right? And the corresponding, let's suppose the orthogonal vector, let's suppose these are orthogonal also. Then you can write Q here, you can write R here, right? You can write R here. You can definitely permute them also. Okay. You can definitely permute them, which means PQR you can write in the permutation also. That's fine. But there is much more thing we can do other than the permutation also. Is this really necessary to write P here? Can you write P plus Q here? I mean, you can take C1 as 1, C2 as 1, and then P plus Q here, right? And then what you can do, you can basically take one more vector and then you can make that orthogonal to P plus Q or something. So basically what you can do, you can if you are writing P plus Q, then or maybe you are writing C1 P plus C2 Q. Okay, let's suppose this is the first vector you're writing here. Then based on the different values of C1 and C2, there are infinitely possible ways to write the first vector itself. Okay, you can normalize it. Normalization is not an issue. But just because of different possible value of combination of C1 and C2, you can write many, I mean, infinite possibility here. Which means, and then you can later normalize. Normalization is not the issue. Which means there are infinite SVDs here. Okay. If the eigenvalues are repeating, in that case, there are infinite SVDs. If the eigenvalues are, all the eigenvalues are distinct. So currently, this is the case when all singular values, sorry, all singular values are distinct. If all singular values are distinct, you just have one single eigenvector, right? There is no choice here. There is no choice at all. Okay, just u1. I mean, the choice you have is just k into u1, but we have neglected that k, right? I mean, that k cannot be any random number. It can be at most -1. Okay. But if you have a choice here, if this is, let's suppose, if the singular value is repeating, if this could be the linear combination of u1 and u2, then there are infinite linear combinations here. See, if it is just cu1, if the solution space is just cu1 corresponding to sigma 1, then I don't have any choice. Okay, just one single unit vector can be there. But if corresponding to sigma 1, if I have, let's suppose this, okay, let's not worry about it. Let's suppose corresponding to sigma 1, I have this. Then what I can do, there are actually infinite possible values of C1 and C2, and then I can normalize them, right? Earlier, if I'm normalizing, then basically, see, earlier, if with just, let's suppose, K into U1, okay, if you normalize, anyway, this K will get cancelled out, right? It can be, after normalization, can be U1, can be minus U1. But let's suppose you have K1 U1 plus K2 U2. Okay. Then after normalization, it will be basically depending on the values of K1 and K2. It will be basically K1 U1 plus K2 U2. Maybe the length of this. So what will the length of this? This cannot be directly K1 square, K2 square. So basically, depending on the length of this, there will be the normalization factor, right? It will be a different normalization. For example, it will depend on K1 and K2. Let's suppose K1 is 2, K2 is 3, right? So now whatever is the length of this, right? I don't know the length of this. It will be divided based on that. If K1 and K2 are different, let's suppose it is 4, let's suppose 5, then whatever is the length of that, it will be divided based on that. So basically, it is not just u1 and minus u1. Now there are different vectors that you can generate from this. Okay, different unit length vectors you can generate from this. Okay, so which means here at the first place itself we have many possibilities. So the conclusion here is that if all the singular values are different, then just two possibilities, right? If any of the repeating, then in that case, since it is symmetric matrix, I mean, it is the eigenvectors are corresponding to symmetric matrix. If it is repeating even two times, then there will be the combination, right? The moment it repeats, the immediately you will be getting the combination, because am and gm both are equal. So which means if it is repeating two times, then there will be combination of two linearly dependent vector. Then here you have multiple choices. Okay, you just don't have one choice. There are infinitely many choices. Okay, in between both of these cases there is one special case when only one of the sigma is zero. Okay, only the last sigma is zero. Other than that, all are distinct. Okay, just see, it is here also. No sigma is repeating, right? No sigma is repeating. Okay, so sigma is not repeating. You have the fixed choice. This can be un or can be minus un. There is no other choice if no sigma is repeating. Okay, there cannot be infinitely many. There's just two choice, but it is just so that it is just so special that you got four more choices. It is little more special. But if sigmas are repeating, okay, if sigmas are repeating, then there are infinitely many cases. So basically, I've taken this question from Stack Exchange, and you can see the answer that if this is distinct, if this is distinct, the moment it is distinct, right? These are distinct. The singular values are distinct. Then you have finite SVDs. Okay, either 2 power n plus 1 or 2 power n. If these are distinct, then you have finite SVDs. Okay, so these are finite. If this is repeated, okay, then there are infinite SVDs. If this is repeated, understood? Okay, so basically you can multiply by minus 1 here and minus 1 corresponding to there also. But if it is repeated value, then you can take any linear combination as one of the vector, and then there are actually infinitely many linear combinations are possible, right? So this is about the number of SVDs. Okay, so for example, this is, I think, some other answer of some question. So, for example, if you are writing u, then they are writing sine of t. Sine means you can take plus ones. It could be the value of this is plus one or minus one, right? You can take u. You can multiply this u as plus one minus one. I mean, it is showing something like that. Don't need to know much, but yeah. So, have you understood the number of SVDs part, right? So there are three cases that I have shown you, or maybe you can say two cases, right? In case of distinct singular values, it is basically, again I'm writing two cases. Okay. Uh, no zero, just one singular value zero, right? So in this case, 2 power n plus 1. In this case, 2 power n. In this case, infinite. Okay, cool. So this is all I wanted to discuss today. Now, like I think we are almost done. PCA, I thought that we can cover in this particular series, but it requires little bit of knowledge of optimization and covariance metrics and these things. So then I finalized that okay, let's just do PCA in machine learning itself. Okay, we will do in machine learning, right? Okay, so that is all, and I think there are small topics remaining, which is partition metrics and quadratic forms. Okay, good. So mostly, like we will be covering them by tomorrow itself, and then we can conclude on linear algebra. So currently, probability is also going on. You can just start watching those lectures, and once you watch all of those lectures, we will start probability module 2. Okay, good. Thank you, everyone.